Hello again. Welcome back to Statistics. Today we're in section 9.2, Estimating a Population Mean. The most important thing I need to show you today is how to construct and interpret a confidence interval for a population mean. But before we can do that, we have to talk about a few other things first. I need to show you how to find a point estimate for the population mean, and we need to talk about students' t-distribution, and I'll show you how to use the t-table to find t-values. Then we can construct and interpret confidence intervals, and then I can show you how to determine the sample size needed to estimate a population mean within a specified margin of error. We've really got our work cut out for us today, so let's go ahead and get started. Now remember, we've said several times that the goal of inferential statistics is to be able to take information about a sample and use it to draw conclusions about a population. So with that in mind, imagine that you need to know the mean gas mileage of a fleet of 10,000 cars. It would be impossible to measure the mileage of all 10,000 cars. It would take forever and it would be too expensive. But you could find the mean of a sample and then use that as an estimate of the population mean. However, since no two samples are alike, we have no reason to expect the sample mean to be exactly equal to the population mean. In other words, every time you take a different sample, you would get a different X bar. So how would you know which one is the true population mean? And the answer is that none of them can be expected to be exactly equal to the population mean, but that sample mean is a good starting estimate. So what statisticians do is, instead of stating that the population mean is equal to the sample mean, they typically state their estimate as a sample mean plus or minus a margin of error. And when we do that, it's called a confidence interval, because we always state it with a level of confidence that tells how confident we are that the population mean is actually in the interval. Now, the first step in constructing a confidence interval is to obtain a point estimate of the parameter. And you might have already guessed that the point estimate of mu is just the sample mean X bar. So let's look at example 1. The website fueleconomy.gov allows drivers to report the miles per gallon of their vehicle. The data in the table show the reported miles per gallon of 2011 Ford Taurus automobiles for 16 different owners. Obtain a point estimate of the population mean miles per gallon of a 2011 Ford Taurus. Well, we know that a point estimate for mu is simply the sample mean X bar. So what you would do is enter these 16 numbers into your calculator and use one variable stats to find the sample mean. I've already done that, so I'll go ahead and say that the point estimate is equal to X bar, which is equal to 36.8. Now here's just a quick note about showing your work. In this section, the main focus is the confidence intervals. So on the show your work problems in MyLabs Plus, you are no longer expected to show your work finding the population mean. We assume now that you're going to use technology to find X bar and S. So on any show work problems that you encounter on quizzes, just show the work for calculating the confidence interval itself, and don't feel obligated to show the work for calculating X bar. Now, after we calculate the point estimate, the next step is to calculate a margin of error, which is denoted by E, and that margin of error is based on the confidence level. So the confidence interval then is X bar minus E to X bar plus E, but we just don't yet know how to calculate E, and don't worry, I'm going to show you that soon enough. Now remember, confidence intervals always come with a level of confidence, and that represents the expected proportion of intervals that will contain the population mean mu if a large number of different samples is obtained. Confidence level is almost always stated in percent form. So for example, A 95% confidence level implies that if 100 different confidence intervals are constructed, each based on a different sample from the population, then we could expect about 95 of the intervals to include the mean, and we would expect that about 5 of them would not include the mean. Let me show you what I mean. Now, I've pulled up the confidence interval applet that comes with your textbook. If you would like to play around with this applet yourself, remember you can open up MyLabs Plus and then click on Tools for Success and then click on Applets. And this is the confidence intervals for a mean applet. So what I've got here is a population that's normally distributed. The mean of our population is known to be 50, and the standard deviation is known to be 10. Now, in practice, when we construct a confidence interval, it's to try to estimate the mean. Here, we already know the mean, so we're really just doing an experiment here to see how confidence intervals work. So in this experiment, we are going to take samples of size n equals 30 from our population, and the computer is going to construct for us a confidence interval at the 90% confidence level. So remember, the confidence level is the proportion of similar intervals that we can expect to contain the true population mean. And again, this population mean is known to be 50. So when I run 100 confidence intervals, I expect about 90 of them will contain the mean, and I expect about 10 of them will miss. So let's actually run 100 intervals here. Now, each of the lines represents a confidence interval. The dot in the center of each line represents the point estimate, and then the interval spreads out to the left and to the right. All of the green confidence intervals are green because they overlap the true population mean mu, but the red ones missed. So notice up here they're telling us that 90 of them contain mu, and we have 100 intervals here, so that means 10 of them missed. That is exactly what we would expect. I can mouse over one of these and just show you. For this particular confidence interval here, the lower limit is 48.516 and the upper limit is 55.088. So definitely 50 is in there. And I can mouse over one of these red intervals, and you can see this red one goes from 44.163 to 49.996. So it didn't miss by much, but it did miss, so that's why it's red. And we can look at this one down here. This one goes from 53.072 to 58.432. So the population mean of 50 is nowhere near this interval. So that's the way it goes with confidence intervals. Sometimes you hit it and sometimes you miss it. And because we know that they're not always right, the confidence level tells us what percent of similar intervals we can expect to contain mu. So I'm going to change the confidence level from 90% to 95%. Now notice that I have right now 10 red lines. When I change the confidence level from 0.9 to 0.95, watch what happens to our intervals. At the 95% confidence level, what happens is the intervals get wider. So now not as many of them miss mu. Notice now we only have 6 red lines. 1, 2, 3, 4, 5, 6. So 94 of our intervals contain the mean and 6 of them missed. So what I want you to get from this demonstration is that the confidence level just tells us what proportion of similarly constructed confidence intervals could be expected to actually contain mu. Okay, now let's go back to our fleet of cars. So this is the same situation we had before, except now it says the sample mean is x bar equals 36.8, and the margin of error based on a 95% confidence level is E equals 1.56. Calculate and interpret the 95% confidence interval. So we know that x bar is 36.8, and we know that E is 1.56. Those were given to us. And remember that a confidence interval goes from x bar minus E to x bar plus E. So first I'll just take x bar and I'll subtract E, so 36.8 minus 1.56 is 35.24, and then I'll take X bar and I'll add E, so 36.8 plus 1.56 gives us 38.36. So our confidence interval goes from 35.24 to 38.36, and that means we can say we are 95% certain that the true population mean is between 35.24 and 38.36. Now, I just want to caution you about one thing. Sometimes people will try to state their confidence interval this way. They'll say there's a 95% chance that mu is between 35.24 and 38.36. The problem with talking like that is that mu is not determined by chance. Mu is a population value. It has a value. It's just that we don't know what that value is. So that value is either between these two numbers or it's not between these two numbers. There's not a 95% chance of it being in there or not being in there. So instead of saying that there's a 95% chance that mu is in this interval, we say that we are 95% certain that mu is in that interval. And that just gets us away from talking about mu as though it were determined by chance. Now that we know what a confidence interval does and how to interpret a confidence interval, we need to start thinking about how we can calculate that margin of error for ourselves so we can construct our own confidence intervals. Now, if we knew the population standard deviation, this would be pretty easy because we could construct, for example, a 95% confidence interval by finding the z-scores that mark off the middle 95% of values. And then we could use that z-score to calculate a margin of error. But remember, the whole purpose of building a confidence interval is to try to trap the population mean between two numbers. If we don't know the population mean, then how likely is it that we know the population standard deviation? It's probably not very likely. So if we don't know the population standard deviation, how are we going to get those z-scores? Well, you might already be thinking that since we don't know the population standard deviation, couldn't we just use the sample standard deviation as a substitute? And that is actually a pretty good idea. But the problem is that although x bar minus mu divided by sigma over square root of n is normally distributed, x bar minus mu divided by s over square root of n is not normally distributed. So we can't really be sure that the z-table is valid. In fact, we can be pretty sure that it's not. Now, this was exactly the problem facing William Gossett in the early 1900s. And I know you're saying, who's William Gossett? Well, Gossett was a statistician who was working for the Guinness Brewery Company, and he was trying to identify the best barley variety for them. Because he was working with actual product that the company needed to sell, he was limited to very small samples. They couldn't afford to let him drill holes and take samples in every keg of beer they produced because they needed to sell it to stay in business. So, Gossett found that his confidence intervals were often incorrect, and he figured that this was because he was working with such small samples. So, he devised a new set of distributions that he called the t-distribution. And it was pretty groundbreaking because they'd never been able to use such small samples before, and Gossett figured out a way to do that. However, the Guinness Company required him to publish his results anonymously because they didn't want people speculating about what kind of experiments they might have been running on their beer. So, Mr. Gossett published his results under the pseudonym Student. And for that reason, lots of textbooks still call this distribution Student's t-distribution. So let me tell you a little bit about Student's t-distribution. Suppose that a random sample of size n is taken from a population. If the population from which the sample was drawn is normal, then this distribution, x bar minus mu divided by s over square root of n, follows student's t-distribution, and it's normally distributed, and it has what we call n minus 1 degrees of freedom. I'll tell you more about that in just a minute. But right now, let me tell you a little bit about student's t. Remember that the z-score tells you how many standard deviations from the mean a number is. The t-statistic tells you how many sample standard errors x bar is from the population mean mu. It turns out that the shape of the t-distribution depends on the sample size n. The larger n is, the thicker the tails are and the flatter the curve will be. You can see that in the diagram here. Notice that in blue we have a normal distribution. The red and the orange are both t-distributions. In the red curve we have a t-distribution with n equals 15, and the orange curve is a t-distribution with n equals 5. Let's look at the red curve for a second. It's a little shorter than the normal curve, but look at the tails. The tail is a little thicker than the tail of the normal curve. And then the curve for the distribution with n equals 5 is even a little shorter than the t-distribution with n equals 15. And look at the tail for that one. The tail for the t-distribution with n equals 5 is even thicker than the tail for the t-distribution with n equals 15, and both of them are thicker than the standard curve. So we see that as sample size gets smaller, the t-distribution gets shorter, but the tails get thicker. Now the t-distribution has a lot of properties in common with the z-distribution. It's very similar, but there are a couple of differences. The t-distribution, remember that the z-distribution was just one curve that we called the standard normal curve, but the t-distribution is different for different degrees of freedom, and we saw that with the two different t-distributions on the last slide. All you really need to know about degrees of freedom is that for students t, the degrees of freedom is always equal to n minus 1. So degrees of freedom is always whatever your sample size is minus 1. Now the t-distribution is centered at 0 and is symmetric about 0, just like the standard normal curve. And the area under the curve is still 1, just like the standard normal curve. As t increases or decreases without bound, the graph approaches but never equals 0, just like the standard normal curve. The area in the tails of the t-distribution is a little greater than the area in the tails of the standard normal distribution, and we saw that with the diagram on the last slide. And finally, as the sample size n increases, the t-distribution gets closer and closer to the standard normal distribution. Now, just a note about notation. You may remember that the notation z sub alpha is used to represent the z-score that marks off an area of alpha to its right. Similarly, t sub alpha represents the t-value that marks off an area of alpha to its right. So if we have a t-distribution and we mark off a t-score, then if the area in the right tail is equal to alpha, then that t-score is t sub alpha. Now, I know you remember learning to read the z-table in section 7.2. Now we need to learn to read the t-table. Because the t-distribution changes for different values of n, its table looks a lot different from the z-table. Remember, there's a different t-distribution for each sample size, but the t-distribution table is not arranged by sample size, but it's arranged by degrees of freedom. Remember, for the t-distribution, degrees of freedom is simply n minus 1. So to use the t-table, what you'll do is find the degrees of freedom you need on the left side, and then find the area in the right tail along the top row, and the t-score will be where those two intersect. Now, if the exact number of degrees of freedom you need is not listed in the table, just choose the closest number available. So for example, if sample size is 44, then degrees of freedom would be 43. But you won't find 43 degrees of freedom in the table. The closest you'll be able to get is 40. So you just go with the closest degrees of freedom you can find. When sample sizes are very large, for example, when degrees of freedom is more than 1,000, then you can just use the z values that you'll find at the bottom of the table. Now here is our first look at the t-distribution, and the first thing I want you to do is notice how different this is from the z-table we've been using. In the z-table you had z-scores along the left side with the hundredths place of the z-score along the top, and in the center of the table you found the areas. The t-table is set up completely different, because remember there would have to be a different t-table for each different sample size. So to keep everything together on one page, instead of giving us access to every different area and every different t-score like the z-table does, the t-table is rearranged so that the areas are along the top, and notice we only have a few of the more commonly required areas. And down the left side you see degrees of freedom. Remember, degrees of freedom is n-1. Now notice the diagram in the upper left corner of the table. This is to remind us that all the areas you see listed along the top are areas in the right tail, and therefore the t-score you get is a positive t-score. Of course, if you needed an area in the left tail, you would just take these same t-scores and make them negative. Now for this example, let's find the t-value such that the area under the t-distribution to the right of the t-value is 0.1, assuming 15 degrees of freedom. That is, we want to find t sub 0.1 with 15 degrees of freedom. So just to help you visualize what we're dealing with, I'm going to draw a t-distribution, and I'm going to mark off t sub 0.1. And of course that means the area to the right of this t-score is 0.1. Now what we'll do is come over to the t-table, find the line for 15 degrees of freedom, and then go across the top of the table and find the column for 0.1, and the t-score we're after is at the intersection of those two, and the t-score we're after is at the intersection of this row and this column, and so t sub 0.1 is equal to 1.341. Now because it's sometimes inconvenient to get your hands on a t-table, I thought I'd just show you how to find a t-score using your calculator. And of course, finding a t-score on the old operating system is a little different from finding a t-score on the new operating system, so I'll show you both, and I'm going to start with the old operating system. So the first thing we need to do is pull up this distribution menu. So we'll have to use the second button to access that menu. We'll hit second and then VARS, which will get us the distribution menu. And the command that we want is inverse T. So that's option number 4. So you can either arrow down there and hit enter, or you can just hit option 4. Okay, now inverse T requires us to tell the calculator two pieces of information. First, you need to say what area you want to the left of your t-score. So I'm going to tell it 0.1, and then comma. Now you need to tell it degrees of freedom, and remember we had 15 degrees of freedom, and then you can press enter. And notice that the calculator gives us a negative t-score. That's because the calculator assumes this area we entered is to the left of the t-score. So it's giving us this t-score that would be on the left side of the curve, and of course that's negative. But remember, the way the table is arranged, it gives you the area in the right tail, which would be a positive t-score. So you'll just have to either be aware of the sign of the t-score that you want, or you'll have to make sure that you're actually entering the correct area to the left. So in order to get the positive t-score, I would have needed to put a 0.9 here, because remember, if the area on the right is 0.1, then of course the area on the left is actually 0.9. Now for the new operating system. And of course with the new operating system they made it a little more user-friendly. But again, we go to the distribution menu, so second VARS. Again, it's option 4. And this time it actually gives us some hints. So all you have to do is put area 0.1, or if you want the positive, you could put 0.9, but it doesn't matter as long as you know what the sign of the answer should be. So 0.1, arrow down, and then degrees of freedom is 15, and then arrow down again and just press enter for paste, and it puts it into the command for you, and then you press enter and run it. And it's going to give us the same t-score that we got before. It's just that with the new operating system, they actually tell you what the information is that you're putting in. And with the old operating system, you have to remember that you put in the area to the left first, and then you put in the degrees of freedom. Now, before we move on, I do just want to remind you that whenever you see this T sub alpha notation, the subscript here is always going to give you the area in the right tail, and you're supposed to be finding the t-score that has that area to its right. So of course, as long as this area is less than 0.5, and it always will be, the t-score that you get here should always be positive. That's why the table is laid out the way it is. The table will always give you the area in the right tail. Remember, the calculator is set up where you actually put in the area to the left of the t-score you want. So you have to be aware that if you are finding a t-score in a T sub alpha notation, that t-score will be the right tail, and it's going to be a positive t-score, regardless of what the calculator tells you. So you just have to be in control, and you have to be aware of where the t-score is that you're trying to find. Now I'm going to go ahead and stop this video, but when I pick up in part 2, I'll show you how to construct your own confidence interval.